Greetings once again. Welcome to another Doppler Effect video. Okay, so here they're saying a car moves at a constant velocity of 22 meters per second on a straight horizontal road towards a stationary device. Okay, so our observer here or listener is going to be this device, which can both emit and detect sound waves. Okay, and then they're saying the device emits sound waves with frequency of 24,000 hertz. These sound waves are reflected off the car, and the reflected sound waves are then detected by the device. Okay, now that's asking us here to state the Doppler effect in waves. So as usual, what we're going to do here is we are going to paste the definition, right? And then what happens is, please use your guidelines when you are revising these. Okay, so Doppler effect, once again, we're talking about the change in frequency of sound detected by the listener, because the listener and the source of sound have different velocities relative to the medium of sound propagation. Okay, so then now this was point one here. This was point one. Let's go to 6.1.2. So here they're saying if the speed of sound in air is 240 meters per second, calculate the frequency of the reflected sound waves detected by the device. Okay, right, now let's see how it goes. Okay, so we need to do this in two stages. Okay, first of all, here we know that this device has emitted like this 24,000 hertz towards the car. Okay, so that means at first the source is this device here. This is the source, then this is gonna be the listener. So we need to know whatever frequency is received by the car here, and then we're gonna take that frequency. Now this is gonna, in the second stage, this is gonna be the source, then this one is gonna be the listener now, that is going to detect these reflected waves. But first of all, let's then first get what waves or what frequency does this car experience. Okay, so we're going to follow our Doppler effect procedure here. FL is equal to V plus minus Vs over V plus minus V. This is actually supposed to be VL and then Vs here, right? Then Fs. That's what we've got here. Okay, that's the first thing that we need to do. So now we need to then decide what is happening here with regards to the signs. Okay, so now at first we know that Vs is stationary. That means it's going to be 0 meters per second, because this is the source. This is the first thing that we are doing. Okay, and then we can then see that, okay, the car is moving towards the device. So that means the velocity here is going to be positive. So that means what you're going to have FL V plus VL over V, just V. Why is it just V? Because Vs is 0. Okay, then this is what we've got here. So then when we move forward, then just substitute, because we are looking for FL. We are going to say V is 340 plus the listener is the car at this point, which is 22 meters per second all over 340 times the frequency that was emitted is 24,000. Okay, this is the frequency that from the source. So now what is the frequency that we've got here? Let's play with our calculator. So I'm getting 25,552.94 hertz. This is what I've got, right? So that means now at this point here we've got this because now this is our source. So since this is our source, it means we've got this 25 here, 552, that is going towards the device. So now we then need to calculate what is the actual device now experiencing after this. Okay, so that means we're still going to take our Doppler effect formula. Let's just change the color here. So what we're gonna have is, this is stage 2. So what we're gonna have here is you're going to have FL is equals to V plus minus VS, VL, sorry, supposed to be VL, and then plus minus VS, then FS. Okay, now the source is going to be what? It's going to be this here, right? But then again, we need to decide on our signs, how our signs are going to be, right? So we know that this now is moving towards, so the denominator has to be less. Okay, please visit one of our videos when we're doing Doppler effect. Okay, right. So now that means you're going to have this here. The listener is at 0 again. So that means you're going to have V here, then here V minus actually Vs times Fs, like so. Okay, so that means what you're going to have is 340 over 340 minus the source now is 22, because the source now is the car, times then our 25, which is the frequency 52.94. Then here, this final frequency is the frequency that is detected here. So let's punch our calculator and see. So then you get 27,320.75 hertz. Okay, this is what you've got here, right? So then they're asking us here, the spectral lines observed on a distant star show that the star is moving away from the Earth. Explain by referring to frequency how you can deduce that the star is moving away. Okay, how do we then go about that? So this one is just simple of your red shifts and your blue shifts. Okay, so how do we then detect here? Let's think about it a bit. Okay, so here in simple terms we can say the spectral lines will then shift or be shifted to the lower frequencies of the spectrum. Okay, then what shift would that be? Would it be a red shift or would it be a blue shift? Okay, that's the question that I'm leaving with you. Cool, guys. Thank you.